Hey everybody, Mr. Piercy here, and what we're going to be looking at in this video are going to be properties of angle bisectors inside of a triangle, and we're going to be looking at how the distances between angle bisectors are used inside of a triangle, as well as talking about the point of concurrency that a triangle uses, which is called the incenter. Now again, as with the other lessons, what I've been trying to emphasize is vocabulary. This unit has a lot of vocabulary. So we've talked about midsegments so far, perpendicular bisectors, and now angle bisectors. Each of those things has certain characteristics about that that you will be responsible for remembering what they are and how to use them in a problem situation that you might see on a quiz or a test. Keep in mind, there aren't going to be notes allowed when it comes time for quizzes and tests. So it's really significant. It's really important for you guys to commit these vocabulary terms to memory. So when you start thinking perpendicular bisectors, remember that that's dealing with the circumcenter. If you hear the word incenter, you need to start thinking about, well, hey, that's going to be talking about angle bisectors. Properties of midsegments, remember, they're parallel and they're half the length of the third side of the triangle. So anyway, that's just a quick review. Just again, please make sure you're paying attention to the vocabulary, because if you have a hard time understanding the vocabulary with this unit, you're going to be in trouble with when it comes time for a quiz or a test. So here, the incenter, the vocabulary term that you're seeing, of course, if you watched the application video where this stuff came from that I made, this is just showing you, again, a diagram of what the incenter is, meaning it's the center of a circle that is inscribed inside of the triangle. Now, also, what we're talking about is how the angle bisector has some similar characteristics to a perpendicular bisector. When we talked about a perpendicular bisector, what we said is that, hey, if I have a segment that is bisecting something, so let's call this point A and let's call this point B. Well, if I have a point here, let's call that point C, because it's on a perpendicular bisector, the distance from A to B has to be the same also. Well, in an angle bisector, it's similar. What you're seeing in the diagrams here in the angle bisector theorem, what it's saying is that if you know where point B and C are, the distance to D from both of those are going to be the same. Now, the catch on this one is, if you notice that they're specifically using the fact that at point B and point C, they have to form a right angle. And the reason why they're saying that they have to form a right angle is simply because you know, in the application video that I showed, that any point along the angle bisector was the same, I knew that the points that I constructed were the same length because I constructed them that way. Well, because we're not constructing the triangle that we're seeing here, or the figure that we're seeing here, where we have angle BAC, because we don't know that B and C were constructed to be the same distance away from A, that's why they're saying that without that right angle, we don't know that point D is going to be the same distance away from B and C. So that's one of the distinct differences here. In the other video that I made demonstrating where the incenter came from the angle bisectors, and that any point along the angle bisector would be the same distance away from a fixed point on an angle, well, I knew where those fixed points were because I constructed them that way. If I don't know that they're fixed points, we want to be looking to make sure that we have right angles, so that way we know it's the shortest distance between 2 points. So the converse says, well, if I know that the distance from B to D and from C to D is the same, and BD is perpendicular to BA and that CD is perpendicular to CA, then we can conclude that ray AD must be an angle bisector of this particular figure. So again, this is going to be kind of a recurring theme that you'll see throughout the course of the curriculum. A lot of times when we have a theorem, we can take the converse of it, and if the converse is true, we can use that as well as far as an application, how we can set up and solve problems. So taking a look at the first example here, find the measure of angle CBE. So again, I'm going to just pretend that the solution stuff isn't there. I just want to look at the diagram because this is what you have to do on your assignments. This is what you have to do on your quizzes and stuff. You don't get that kind of framework to help you think your way through the problem. Well, how can I figure out the measure of angle CBE? Well, we have some important information here. The fact that they're showing me that at point C, that ray CB is perpendicular to CE, and also that DE is going to be perpendicular to BE. Because those are right angles and CE is congruent to DE, then it must mean, according to the converse of the angle bisector theorem, that BE, ray BE, has to be an angle bisector. So if ray BE is an angle bisector, then that means angle EBD and angle EBC has to be the same length. I'm sorry, not the same length, but the same measurement. So that means angle CBE must be 31 degrees. And that's exactly kind of what we're going to be looking at here. So think your way through the problem, use the ideas, use the concepts that are presented in the notes, and if you had to write an answer like this as a say a free response question, I would be checking to see, are you using the appropriate vocabulary? Are you telling me, well, because these angles are right angles and the distances are the same, according to the converse of the angle bisector theorem, ray BE must be an angle bisector, therefore we can say that these angles are the same. Here in example 2, even though it says this is a real-world problem, this is a very kind of odd question in my opinion. I get the idea what they're going for with it. So here we have a spider web. And so the fly, which it looks like it's an A, but here's the fly. The fly is flying towards the spider web. So you can go this way, he can go this way. You can go left or you can go right. But say he's going to get trapped in the spider web. Well, where should the spider sit? Will the spider have to move further? You know, what we want to know is that we just want to understand that the spider, he wants to be uh, along the angle bisector created between the spider and the fly, because it doesn't matter where the fly lies or where the fly lands, if he lands to the left or to the right of the spider, as long as as long as the distance between them is the angle bisector between where the fly is and where the fly could go. When the fly lands on the spider web, it will be the same distance away from the spider no matter where it lands. And that's kind of what we're looking at here. So this is an okay question. I mean, it's really just saying, okay, well, just understand the idea that anything from the angle bisector really should be the same distance away from a fixed point. So that's really what they're kind of asking you to understand there. It's not the greatest example in the world, I'll give you that, but it does illustrate the point, what they're talking about with angle bisectors. So now here, we're still looking about an angle bisector. So the question says, for what value of x does is P going to be lie on the angle bisector of angle J? So if, let's go ahead and put something here. So let's say we have a ray JP, and we want to know, well, how do I know that it's going to be an angle bisector? Well, first of all, these segments KP and LP, they would have to be congruent to each other. And we'd also want to know probably that we have right angles here. But if the segments are, or point P is on the angle bisector, then the segments have to be the same. So I'm going to say that KP and LP are congruent to each other, therefore x plus 1 is equal to 2x minus 5. And that's how I'm going to start setting up my equation here. So we'll just say, solving for x, we'll take the x on the left and we'll move it to the right through subtraction, and we'll take the 5 on the right and move it to the left through addition, and that is going to give me x to be equal to 6. So that's what the value of x would have to equal in order for point P to lie on the angle bisector of angle J. So here is what we're talking about for the point of concurrency, the incenter. Remember, the incenter is the center of an inscribed circle. Now, I'm going to see if I can, let me see if I can get my compass to work here, and see if we can draw this in here. What they're telling you in this diagram, and that looks all right there. What they're telling you in the diagram is that if the incenter is the center of an inscribed circle, well, then the distance from the center of the circle to each side of the triangle should be the same. Therefore, segment PF, segment PD, and segment PE should be of equal length. And I missed this circle there, but you can see what it should have looked like. Let me see if I can make it a little bigger and actually fit. That's a little bit better. That compass isn't, the electronic compass isn't nearly as precise as I would like it to be, but that's essentially what it's telling you to do. Well, because the distance between them, distance is always going to be, the shortest distance between 2 points is always going to create right angles. So you can see what we're working with is that we actually have some right triangles in the figure that we can work with. So I might have a right triangle here, I might have a right triangle here, something like that. Because those segments have to be the same length and they create right triangles, that allows us opportunities to exploit it, like what we see here in example 4. So here it's telling you that point L is the incenter of the triangle, and we want to know how long is segment LK. So this is the segment that we're looking for right here. How long is that segment? Well, looking at the diagram itself, we don't see any like adjacent sides or anything in triangle, say LJK. We don't really see anything there that allows us to find it directly. However, if you notice, we have a triangle right here that does have 2 of the 3 sides given to us. So because this angle here, JIL, because this angle here is a right angle, this angle here must also be a right angle because they're a linear pair. So that means triangle HLI is a right triangle. And if point L is the incenter of the triangle, then LI and LK have to be congruent to each other. So I can use the Pythagorean theorem between the 15-unit long segment and the 12-unit long segment, and I can find the length of segment LI. And since LI and LK are the same length, once I know what LI is, I've solved the question and I found what the length of LK would be. So that's how we're going to think our way through the problem. So now let's start actually setting up the Pythagorean theorem. Remember, the Pythagorean theorem is a squared plus b squared equals c squared. So what I'm going to do is I'm going to substitute the segments that we know. The hypotenuse is 15. The length that we're solving for in the red triangle is Li. And the third side of the triangle that we know is 12. So solving for Li, and I hit the wrong thing. That should be squared here. So when we square 15 and we subtract 12 squared from it, we get 81. Well, 81 is equal to Li squared. So I take the square root of both sides and I get the length of Li to be 9 units long. And so Li and LK are the same length, so that means both of them are 9 units long. So that's one of the ways that we're going to be looking at how we'll use the incenter to solve a problem inside of a triangle. So now here we are pretty much to the end here, I believe, and I want you to go ahead and try answering these 4 questions here based on the properties of angle bisectors that we've discussed. And once you have your answers, go ahead and unpause the video and come back and compare your answers to see how you did against me. And if you have any questions, this is where you need to make sure that you're writing them down so that way you can send them to me either in the comment section or in the Google Classroom, or through email. So go ahead and pause the video, and when you're done, come on back and see how you did. Okay, so problem number 1. So again, these are the kinds of problems that you're going to see similar to on your homework assignments, on your quizzes and stuff like that. all the framework has been taken away. We have to think our way through the problem. So what we're looking at in problem 1, because we have right angles here and the fact that the segments are congruent to each other, it must mean that this segment here that's not named, or that ray I should say, it must be the angle bisector. Therefore, the two angles are going to be congruent to each other. So I say 3x minus 5 is equal to 2x plus 5, and solving for x I get 10. So now here, looking at the diagram, again, I know that this ray right here must be an angle bisector, really because of this right here. They're showing me that the interior angle has been cut into two equal parts. So that means 7x plus 3 must equal to 8x. And there we go. Solving for x, I get x is equal to 3. So now here in problem 3, do you have enough information to conclude that AC bisects DAB? Now, quite frankly, I would accept both answers of either yes or no, depending on what your explanation was. So here's the answer that I put based on what we saw earlier. The reason why I'm going to say no here is because angle CBA and CDA, we don't know if they're right angles. Now, I could be convinced that if you were able to say that point B and point D were constructed to be the same distance away from A, and this angle were the same, then I would be convinced that ray AC would have to be an angle bisector because CD and CB are the same length. But because we don't know that point B and D were constructed to be the same length away from A, and that we don't have perpendicular angle, or we don't have perpendicular segments to make right angles, I'm going to go ahead and say no on that one. But I could be convinced to say yes. So the last one here, going back to the last example, example 4, the one with the right triangles inside of it. Suppose that you were not given HL or HI, but that these segments, JL and JI, were 25 and 20. Could you find segment LK? Well, very similarly, what we're going to do is we're going to be looking to see where do I have where do I have right triangles that I could exploit. So based on the information that they're giving me, again, I still know that LI and LK have to be the same length. So using the segments that we have, JL is going to be the hypotenuse of a right triangle. JI is going to be the one leg of the right triangle. So we can use the Pythagorean theorem to find that LI is going to be 15 units long. And this is just a little typo here. One shouldn't be. I'm just saying that because Li is equal to length Lk, Lk must also be 15 units long. So that's all we're going to be looking at for angle bisectors for the time being. Okay, so again, just to quickly review, vocabulary, make sure you're paying attention to it. If I say the word angle bisector, you need to automatically start thinking about an incenter. If you hear the word incenter, but conversely, you need to start thinking about angle bisectors. How do I tell if an angle is actually being bisected? Well, we need to know that the segments between the sides of the angle and what we think is the bisector, we need to know that they're congruent, and preferably if they're perpendicular to the sides of the angle. Or the converse is that if I know these segments are the same length and the segments are perpendicular, then it must create an angle bisector. So any questions that you have, again, make sure you write them down, send them to me in the comment section of the Google Classroom, or send them to me in an email. Until next time, guys, thanks for watching, and take care of each other, okay? Bye.